In this video, we're going to be looking at the length of a line segment, and which is the second part of this question. And the length of the line segment can be derived using this distance formula. So I provided the distance formula here. So we have the distance. So this d in front of the parentheses is saying the distance, d, distance, between 2 points, P1 and P2, is defined as the following formula. And we have the same sort of notation with x1, x2, y1, y2. And so let's go into this. Now, before we do, just to understand a graphical understanding of what's going on here, we could look at this graph at the same points as what we discussed in the previous video. So we can look at this, and the distance between 2 points is just the length of this line I've sketched right here. So that's what we're measuring. We're measuring the length of this line. So there we go. It's that length right there. That is defined as d P1 comma P2, where P1 and P2 is it's these 2 points right here. Okay, so yeah, let's go into this video, or this example, this part of the problem, and we have dp1 p2. So dp1 comma p2. Now you may be somewhat familiar with this formula here if you think about it, and I'm sure a lot of you have heard of this name. Maybe some of you have not, but it's known as the Pythagorean theorem. The Pythagorean theorem, I'll write it down. So the Pythagorean theorem is it has to do with the right triangle, and we have A, B, and C, and we can derive the following formula: a squared plus b squared equals c squared. So realize we have something squared here plus something squared here, and we've taken the square root. So if you were to square both sides right here, you would end up with this formula in general. And you'll notice that you can kind of see a triangle here. So essentially we're solving for C. That's our dp1b2 that we're looking at here. The length of that line segment is like our C here. So anyways, just to show the parallel, well, let's go into it. That's where this general formula comes from. So back in the Pythagoras days, you know, it's really old. This has been around for a long time. But anyways, yeah, looking into this. So what we have here is x2 minus x1. So x2 is 4 minus x1, which is -4. So you got to keep track of the signs. It gets a little confusing, but notice it's minus x1, and so it's minus a negative number. And then we're going to square that, as mentioned here. We're squaring that entire thing, and then we're going to add y2 minus y1. So that's -2 minus 3 squared. We're going to square that too. Okay, and that's what we have here. So we just need to simplify this. Okay, and so we have 4 minus a -4. So that's minus a negative is like a plus. So it's like 4 plus 4. So that's the square root of 8 squared. And then plus -2 minus 3 is -5 squared. Okay, and we have square root of, that's 64 plus 25, and that gives us the square root of 89. So that is the exact solution. You may be asked to round this to so many decimal places. So you can use your calculator for this. So the square root of 89. And let's just go ahead and round this to 2 decimal places. So this is approximately 9.43. And if any was given in this in the problem, you would want to include units. So if we're talking about inches, or you'll want to input that after your solution. But in this case, we have no units, so 9.43. So what we're saying here is that the length of this line segment right here is 9.43. Notches away. So you may be wondering why we do x2 minus x1. Realize that the distance between here and here is this coordinate minus this coordinate. So it's x2 minus x1. And then this is similarly y2 minus y1, the distance from here down to here. So that's how we have a squared plus b squared equals c squared, because of the length of each of these sides. All right, let me know if you have any other concerns. I'll be more than happy to help. All right, thanks.